Cool? Super cool. Okay, last one, we're not pausing. Hydrogen bonds are the strongest intermolecular force that we're going to deal with. And not to be annoying or confusing, but a hydrogen bond is not a bond. It's an intermolecular force, okay? Technically, the word bond means that it's permanent and it forms a new compound. A hydrogen bond is not an attraction that makes a new compound, so it's kind of a misnomer. Sorry about that. I didn't get to name it, though. But we still call it a hydrogen bond. But it's an attraction between hydrogen atom bonded to a highly electronegative atom, one of these three, and nearby an electronegative atom. I'm going to draw you a diagram to kind of explain what this first sentence is, okay? You don't necessarily need to write the second part here. Just know that it's not actually a chemical bond. We just call it a bond.
Wait, so for this, is it only with those three?
It's only those three elements, yes. It doesn't work with other elements because they are not electronegative enough. Okay, so if I were to give you kind of a generalized diagram of this, okay, a hydrogen bond occurs between a hydrogen atom that is bonded to one of these elements, okay, so it is covalently bonded to one of these, and then is also nearby one of these three elements bonded to something else. Okay, so this is a general,
Does it have to be
generic way.
like for the X? It can't be hydrogen.
It could be.
Oh, okay.
It could
So
be, but it doesn't have to be. Just the point is you've got something out, one of these nearby. Okay, and so the hydrogen bond is going to be an attraction between this hydrogen and these. Okay, now if I have hydrogen bonded to one of these, that will be a polar bond. So there's a dipole here. Okay, and then the assumption is that this will also be a polar bond. Doesn't have to be, but generally it probably will be. And so we can see I've got partial negative, partial positive, partial negative, partial positive. This is where this attraction comes from. Okay? So it's kind of a dipole-dipole interaction, but it's super strong. It's a very specific type of dipole-dipole interaction. So it's strong enough that it kind of gets its own category. And it only involves a hydrogen atom in the middle. Okay, a classic example of this would be, would be water. Water can hydrogen bond with itself. Okay, there's water molecule. Or actually, I'm going to rotate it, sorry. Okay, so here I have hydrogen bonded to a highly electronegative atom, like this. I have this situation right here. And if I were to have another water molecule over here, just hanging out doing its thing, okay, it doesn't matter what this oxygen is bonded to. The fact is I have a highly electronegative atom right here, and it will be attracted to the slightly positive dipole moment that this hydrogen atom has, okay? Because we have a polar bond here, so this is slightly positive. This oxygen is going to be slightly negative, so I have an attraction between them. Okay, it's not a full-on chemical bond. I'm not making a new molecule, but it's a strong attraction that is significant. Okay, and the cool thing about water is this oxygen can form two hydrogen bonds at the same time. Okay, so any given water molecule can be involved with 4 hydrogen bonds at the same time. So I could have one here, and then I could have another water molecule over here, and it could attract to that one. So this water molecule right there has 1, 2, 3, 4 hydrogen bonds happening. Okay, so water is like super hydrogen bonder to the max. Need some hydrogens here, but you get the idea. Okay, does this kind of make sense? Another example of this could be ethanol. Okay, I'm gonna abbreviate ethanol, CH2, CH3, OH. Okay. Okay, so I have hydrogen bonded to an oxygen. Okay, so that there's potential for that. If I have another ethanol over here, and here I'll draw this one correctly, like a Lewis structure. Okay, so this is just that kind of abbreviated. Highly electronegative atom here, hydrogen bonded to a highly electronegative atom, I can get a hydrogen bond right there. Okay, so just another example of what that could look like. What if I had this? This is methanol. Oops. I forgot what I was drawing. Processing pending. That's what I wanted. Sorry. Not methanol, methane. I wanted that one. Sorry. Will that hydrogen bond?
No,
Why not?
because it's a
Other
carbon.
one more positive on
That's a carbon right there, not a oxygen.
And that's a problem, yes.
Or
The
what?
hydrogen in question has to be bonded to a highly electronegative atom in order for this to work. Yes, I'm nearby a highly electronegative atom, but this is a nonpolar bond, and so this hydrogen is not positive enough to be attracted to that slightly negative oxygen. So I don't see any hydrogen bonding in this situation. Okay? If I had ammonia, now I am bonded to something that's highly electronegative. I do have a polar bond there. Now I can hydrogen bond. Okay? So there's a lot of things to keep track of. I need a hydrogen, but it has to be bonded to the correct element, and it has to be nearby another one of those correct elements in order for it to work. Okay? Kind of makes sense how this works? Okay? Hydrogen bonding is very significant because it's the strongest intermolecular force. It has a very significant effect on the physical properties of different molecules. Okay, so stronger than LDF and DDI. Okay, leads to higher boiling points of compounds and accounts for the heat capacity and crystal structure of water. Water does a weird thing. Here, I'll let you write that down and we can talk about it. Water is a strange compound because it does something unusual when it freezes. Do we know what happens to the density of water when it freezes? Yeah, it expands. The density goes down. Normally when you freeze things, it gets more dense. Water is weird because it gets less dense. It expands when it freezes. The reason it does that is because of hydrogen bonding. When the water's a liquid, all of the molecules are moving past each other really fast and they're not able to really settle into those hydrogen bonds. But if you cool it down enough and things slow down, the water molecules are not moving enough where they can actually get aligned, and they want to align so that all the hydrogen bonds are in a crystal structure. And so once it freezes, they actually spread out so they can align their hydrogen bonds with each other and makes that crystal structure of ice. And so because of those hydrogen bonds wanting to get aligned, that's what pushes all of them apart from each other, and you get less dense ice than what water is. Okay, so hydrogen bonding is the entire reason that water becomes less dense, why it makes the crystal that it does. It's high heat. It can hold a lot of energy. It takes a lot of energy to change the temperature of water. Has a high heat capacity. It also affects the boiling point of other compounds. So if I have a compound and I want to boil it, what happens to all the molecules when I'm trying to boil something? What are they doing? Vibrating faster, and then when it actually starts boiling, they don't just vibrate, what do they do?
Turn the gas.
Goes to a gas, they fly away, right? If I'm boiling a pot of water, the water doesn't stay in the pot, it literally flies out of the pot into the room.
Yeah.
So why would having hydrogen bonds increase the boiling point for a material? How does that make sense? If I have hydrogen bonds, why does that increase the boiling point?
Since the bonds are stronger, to just take more for it to lighten.
Yeah, exactly, that's it. Because there's more attraction between the molecules, it takes more energy, higher temperature to get them to separate from each other and boil. Having this intermolecular force of a hydrogen bond will increase the boiling point. Okay? So it's kind of cool how we can predict the relative boiling points of different compounds just based on what intermolecular forces it has. Okay? So let's kind of summarize here. Do I want to do that? Nah, we'll do this in order. I feel like I want to do these out of order, but it'll be fine. Okay, so to summarize, okay, if I were to make a spectrum of attraction between atoms, the strongest attraction we can have is an ionic bond. Okay, where I have literally ripped electrons away from an atom, put them on a different one, and I have a fully negative charge attracted to a fully positive charge, highly attracted. So an ionic bond is the strongest attraction we can have. Yes?
Is this the last slide?
There's one after this. Okay, that is followed by a covalent bond, and there is some overlap between these. There's some weak ionic bonds and some strong covalent bonds. Okay, but the main point here is that a chemical bond is the strongest attraction between two atoms. Okay, below that we have intermolecular forces, and they are ranked. Hydrogen bond is the strongest, dipole-dipole, London dispersion force. Okay, so if we were to make a little spectrum of attraction, this is what it is. So I don't know, we could almost take, we had our like electronegativity difference where like ionics on this and then covalent. With intermolecular forces, we're like going off the spectrum, and there's even weaker forces that attract atoms. They're not bonds, but they're still significant enough that we care about them because it affects the physical properties of different materials. Okay, we okay with this? Wait a second, okay. Okay, last thing. Okay, let's tie this into physical properties. Okay, boiling point. We've talked about this. Okay, you don't necessarily have to write this down unless you need to remind yourself how boiling works, which is fine if you do. Okay, larger molecules have higher boiling point because of London dispersion forces. Okay, so I'm just connecting this back to what we already know. Okay, molecules that have hydrogen bonding have higher boiling points. Okay, ionic compounds have higher boiling points than covalent compounds because they're more strongly attracted to each other. Okay, so honestly, you could just summarize this, all of these 3 points, as if you have stronger or more intermolecular forces, then you have a higher boiling point. So maybe you have two compounds and one of them has London dispersion and dipole-dipole, and then the other one only has London dispersion. Well, the one with the dipole-dipole will have a higher boiling point because it has another intermolecular force that's holding it together. Okay, so we can just compare them. Okay, this also affects things like viscosity. Viscosity is a measure of how runny something is. If it's very gooey and slow and doesn't flow easily, that's a high viscosity. If it's very runny and fluid, has a low viscosity. Okay, stronger IMFs means you are more viscous because it holds together more. It's more gooey. Okay, kind of makes logical sense. Cool? Not cool? Okay, that's the last slide once you get it written down. I have a worksheet. It is not entirely homework. You can work on it a little bit in class. I will give you class time tomorrow to work on it as well. So don't feel like you have to do the whole thing tonight unless you just really want to. I won't stop.
You only gave us one. Oh, okay.
Yeah.
Alright, alright.